This example is a design example. We have a spherical pressure vessel that's 45 foot in its internal diameter, which already tells us that it's of an industrial size scale, and the internal pressure is 400 psi. Again, that's of an industrial scale to it, right? We're using steel that has an 80 ksi yield strength, and we want a factor of safety that's at least 3 with respect to that, right? And we want to find out what the minimum thickness is, and then increase that to the nearest quarter inch for the design of our steel, or rather of our tank, right? So there's a couple of things we'll do right off the bat. We're going to assume and then check later that thin wall pressure vessel theory applies. Right, so that's D over T is greater than 20. So that's a basic assumption that probably is reasonably safe, but it is an assumption nonetheless. Right, so let's find our allowable stress. Right, and so sigma allow will be equal to our minimum factor of safety times our yield stress. Or rather, that's kind of goofy, isn't it? I'm going to make the allowable greater than the strength. That can't be. That's right. So how do you correct that? Well, we want to reduce it. We want to divide by that. Right? So we want something smaller. So we've got 80 ksi divided by 3. And that's not going to be a convenient number. So I'm just going to leave it as 80 divided by 3. Oh, you're going to want to know, aren't you? All right, so 80 divided by 3, it's not quite 30. It's 26.7 or 26.6. Repeating. Well, you're making all kinds of mistakes. Yeah, all right, whatever. Late at night. Actually, it's early in the morning. All right, so let's find then our sigma max. All right, it's a thin wall pressure vessel, we assume, and it is a spherical one. So that means our basic model is sigma equals pi d I over 4t. And that's your sigma max, and because it's the same in all directions, right? So that means that our t would be equal to p times di over 4 times sigma max. Right, so that's going to allow us to find our T min. That will equal our 400 psi times our internal diameter, 45 feet. Let's get that into inches. And then divide that by 4, and what do we have here? 26.6 KSI, so times 10 to the third PSI, right? So I'm setting sigma max equal to sigma allow is what we've done there. Right. And when we work that all out, what are we going to get? $400 times 45 times 12 divided by 4 divided by 26.6 thousand. I did that math wrong. 400 times 45 times 12 divided by 4 divided by 26,666 equals 2.025 inches. Oh, that's too bad. Not quite 2 inches, so we're going to have to increase that. So our then selected wall thickness is going to be then 2 1/4 inches. Now, If you can convince somebody to use a slightly smaller factor of safety than 3, then it won't be very much smaller than 3, then we can use 2-inch wall thickness, and that probably is actually kind of a big deal. Now we also want to, though, check to make sure that our thin wall pressure vessel theory still applies. It will, right? D over T is going to be 45 feet times 12 inches to get all in inches, and then divide by 2.25 inches. 5 times 12 divided by 2.25, and that's 240, and that's greater than our required 20, and so that would seem to be appropriate. Now, when you start looking at some other aspects of this thing, you are going to have some issues. That's a pretty large diameter to thickness ratio, getting kind of thin, and I start getting concerned about what happens at exit points, access points, and also at support points. That could be a problem here. It just bears monitoring and taking a closer look at those specific locations, but you need a more complex theory to be able to model what happens there.